All right, so what we're going to do is we're going to look at the periodic table and see if we can determine the number of valence electrons. And electrons, valence electrons, the word valence comes from the Latin word vale, which actually means goodbye. It means farewell. It was the Romans' way of saying so long, and we use the term in chemistry because these are the electrons the atom is capable of losing. They are the electrons in the outermost shell, which for us means the electrons with the highest N value. And it's important to know that we can tell how many valence electrons an atom has of an element based off of its position on the periodic table, but we group them by sort of three different groups. In the S block, the valence electrons is equal to the group number. Man, you just gotta love those S block elements, right? Always easiest to tell what ion they're going to form. Group 1 always forms +1, group 2 always +2, and it's easy to tell how many electrons they've got. Group 1 always has 1 valence electron, group 2 always has 2 valence electrons. And while I'm here, I'm going to point out, right, there's a hole. Oh my goodness, what the heck happened there? That was weird. There is a hole right here in group 2 because helium actually belongs in the S block elements. Remember that, especially where electrons are concerned, right here. Helium has 2 valence electrons. All right, so from the S block, we will now go to the D and F blocks. If you look at the electron configurations of any element in the D or the F block, it always ends the same way. It always has the highest N value is always an S, and that's always the only electrons that it has are the S. So, for example, uranium is 7s2 and then 5f4. Well, the 7s2, those are the valence electrons. The F electrons are never valence electrons. D electrons are never valence electrons. So for all of those, there are 2 valence electrons. So sort of like the ions before where we were talking about transition metals, rare earth metals, you can't tell what their charge is. You got to figure it out by the Roman numeral. Same story here, right? They always have the same number of valence electrons. D and F block elements always have 2 valence electrons. Last but not least, definitely not least, in fact, the most complicated is the P block. But it's not very complicated. If you look at carbon, carbon ends in shortcut with 2s2, 2p2. Excuse me. Antimony ends it with 5s2, 5p3. So carbon has 4, and it's in group 14. Antimony has 5, 2 plus 3 is 5, and it's in group 15. So guess what? Oh my goodness. Not sure what's going on here with my whiteboard, but man, it's loving me. For the P block, the valence electrons, the number of valence electrons it has, is equal to the group number minus 10. Right? So if you want to, you can just look up here and you can just cover up the 1 at the top. That tells you how many valence electrons are in each of these things. All right? So now the next most important thing we've got to do, I got to erase my board a little bit here. Doggone it, where are these things are just jumping out at me here? It is having a hard time. My whiteboard is struggling right now. Really, really struggling. Man, it's just pulling random stuff out of nowhere. It's super weird. All right. Try and wrap this video up as best we can. All right, Lewis dots are what we're going to use this information for. Lewis dots. All right, we're going to draw some Lewis dots. So Gilbert Newton Lewis came up with this idea. And actually, he came up with it as a part of getting his PhD and went in front of his committee and he defended the idea to them. He suggested the idea to them, and they laughed at him. And they failed him and made him come back and come up with another idea and present it to him. But the joke's on them, because here we are over 100 years later, and every chemistry student learns about Lewis dots. So anyways, what we do is we take the symbol of an element like carbon, and we imagine that symbol is encased in a square. Now, ideally, it's a perfect square. Mine is never a perfect square, but it's good enough. It's got 4 sides to it, right? There are 4 sides to carbon. And the rules for Lewis dots are as follow. Number 1, there is a max of 2 dots per side, right? So you are never going to have more than 2 dots on a side. Rule number 2 is the left side is first. So you're going to put 2 dots max on the left side. And then rule number 3 is 1 dot on each side, each remaining side, I should say, before doubling up. So this goes back to the old Hund's rule, where we used to, remember, if we had multiple lines, you had to have 1 up arrow in each line before you put a down arrow. So it's the same story here. So carbon, we look at carbon, we see it's in group 14. That means it has 4 valence electrons. So we're going to represent those electrons with dots. So, excuse me, we're going to put 4 electrons on here, and an electron's going to be a dot. So maximum of 2 dots per side. And we start with the left side first. So I'm going to put 2 dots on the left side of carbon. Now, on the other sides, I have to put 1 dot on each side before I can double any dots up. We'll only have 4 dots to put, so I put 2 on the left, 1 on the top, 1 on the right. Could you have also put 2 on the left, 1 on the top, and 1 on the bottom? Absolutely. Could you have also put 2 dots on the left, 1 on the right, and 1 on the bottom? Absolutely. Any of these 3 all mean the same thing. What you are not allowed to do is you're not allowed to forget that the left side fills up first and just put 1 dot on each side. The usual convention is these are the s electrons, and so we put 2 dots on the left because there are 2 s electrons, and then the other sides are the p electrons. So you try it for something like sulfur, for example. I'm pausing, by the way, so you can try and draw sulfur. How many valence electrons would it have? It has 6 electrons because sulfur is in group 16. 16 minus 10 is 6. So we got to start with 2 dots on the left. That's 1 and that's 2. We now have 4 dots left because 6 minus 2 is 4. And so we have to put 1 dot on each side.
Good afternoon, staff and students. We have the results of today's...
All right, so where was I? Oh, yeah, 1 dot on each side before we double up any dots. So there's my 4th dot goes right there. I like to put mine on that side because I want it symmetrical. But remember, what the key here is you got 2 dots on one side, 2 dots on another side, and then a single dot on the remaining 2 sides. So you could have drawn your sulfur like this. Doing a little better on my dots. Or you could have drawn your sulfur like this. Any of these is an acceptable way to draw it.